Hey there, welcome to Chemistry Week 7. This week we'll be beginning Chapter 4 and working through the first half of that. All right, so Chapter 4 is looking specifically at aqueous chemistry. Okay, so let me put that on there, aqueous chemistry. And aqueous chemistry or aqueous solutions and reactions means that we are always going to be dissolved in water. Okay, that's what aqueous means. Okay, so let's take a quick moment and actually do some definitions. And usually I just ask you guys to read the definitions, but now let's go ahead and talk about it just a little bit. The first thing that we're going to be looking at is the term solute. Okay, and the solute is the substance being dissolved. I'm not going to write down what's on the slides because you guys can read that. So the solute is the substance being dissolved. The next term that we have is solvent. And a solvent is the substance doing the dissolving. So let's imagine that we have a beaker. Okay. And in our beaker, we have some water. Okay, and there's our water. And then we put some salt into it. And our salt, we'll just call normal sodium chloride table salt, NaCl. Okay, and our solvent here is water, H2O. Okay, now when we put our salt or our solute into here, it comes apart and we'll have sodium ions and chloride ions and sodium ions and chloride ions and sodium ions and chloride ions all floating around. So that's one example of a solute in a solvent. Okay. Next, it goes into the idea of defining electrolytes, non-electrolytes, and those. And I think those are things that are really easy to read. So I'm going to go ahead and go from this point to the first thing that is really important mathematically in here, and that is the concept of concentration. Concentration basically is how much of your solute you have dissolved inside your solvent. And there are actually quite a few ways to describe concentration. You'll learn more of them in Chem 2. But in this class, we're going to focus on molarity. Okay, and the molarity is often depicted as an uppercase M letter. And you don't want to use a lowercase or a little m because that's molality, and so that's different. You won't get them mixed up in this class, but if you go on to Chem 2 or into other things, that small m means molality, not molarity, and you don't want to mix the two of them up. Okay, so molarity is specifically moles solute per liters of solution. Okay, now before I go any farther, I have my periodic table and my handy dandy ion list here. Okay, and I'm going to pull those out because we're going to be using them all throughout today. Okay, so let's think about that, that example that I had on the previous slide of sodium chloride in water. So we have our NaCl in water. Okay, so let's say that we take, first of all, before I go on any further, I'm going to go ahead and calculate real quick the molar mass of sodium chloride, and that's 1 sodium, 22.990, plus 1 chlorine, 35.45, and that gives me, for my sodium chloride, 58.44 grams per mole. Okay. So if I want to make a 1 molar solution of sodium chloride in water, then I need 1 mole of NaCl per 1 liter of solution. And usually the way you do that is you measure out your solute, you put it into your beaker or your Erlenmeyer flask or a volumetric flask, and then you add water to make 1 liter. Okay. So what we could also find for this would be to use this here. It's supposed to be an arrow there. And this would be 58.44 grams of NaCl in enough water to make 1 liter. However, it's all about ratios, moles to liters, not really fractions, okay? So the other thing that we could do is we could say, well then, remember that 1 liter is equal to 1,000 milliliters. So we could also say that this is the same as saying 5.844 grams in 100 milliliters of solution. Sorry. Okay. And this would still be a 1 molar solution. Okay, so let's work through a couple of options. Okay, so let's say that we want to make a potassium phosphate solution. So here we have potassium phosphate. In water. And we want to make, I'm doing this backwards from what is in the slides a little bit, just so that it's a supplementary. Okay, so we want to then, make, let's say, okay. And what we're gonna make is a 3 molar solution. Okay, and we want to know how to make that. Okay, so in order to find that, let's go ahead and take a look at some of our steps. Here's our step 1. In this case, it's to find our formula. Because you have been given the solute by name rather than formula. So that's our first step. And of course, we're going to do that by using our ion list. And again, you cannot look these up online. Even though this is not what we're studying in this chapter, you cannot type in formula for potassium phosphate and look it up that way. You have to use your ion list. Sometimes I won't be able to catch you, but sometimes I will. So use the ion list. Okay, so potassium ion is K+, and the phosphate ion is PO4 3-. So again, if we have 3 negative charges, we need 3 positive charges to balance them out. And so this becomes K3PO4. Okay, and actually I'm gonna add to my problem here. We need to make 3 molar solution, and we need, just trying to make myself, okay. So we're gonna make a 3 molar solution, and let's say that we need 2.5 liters of it. All right, and you would of course be given all that at the beginning. Right now we're just kind of showing things. Okay, so now our step 2 is, see how we have a molarity here, and we have a volume here. So our step 2 is to solve for number of moles. And actually, let me go ahead and write that out. Solve for moles. And we're going to use the formula that molarity is equal to moles per liter. Okay, and that means that our number of moles is equal to molarity times liters, or times our volume in liters. So then we'll say, okay, then the number of moles of potassium phosphate that we have is equal to 3.00 molar times our volume in liters, 2.50 liters. And the reason for that is that instead of writing molar, I could write this as moles per liter. So molar, that capital M for molar, stands for moles per liter. And if I think about it like that, then you can see that I can cancel out my liters here and I'm left with moles. And that's how we know that we can find moles in this method. Okay, so 3 times 2.5, if you're sleepy like me. Okay, this I can have 3 significant figures, so I have 7.50 moles. Okay. Now my step 3 in this case, because I'm making this formula, is to solve for mass. And we always solve for mass from moles by taking our number of moles and multiplying it by the molar mass. So we have 7.50 moles times the molar mass of potassium phosphate, so 1 mole of K3PO4. Now, in order to find this, again, I need to turn to my periodic table, okay? And I have 3 potassiums, so 3 times 39.098 plus, oh, I think I typed that in wrong. 39.098 times 3, there we go, okay, plus my phosphorus, which is 30.974, plus 4 oxygens, 4 times 15.999, okay, and the answer that I get for this is 212.264. And that's grams K3PO4. Okay, now I can multiply this by 7.5. All right, now I'm getting a huge number, okay? And I can only have 3 significant figures, see? So my answer here is going to be 1,590 grams, which is about 1.5 kilograms, okay? So now what I need to do is, well, and this is sort of part of this. I'm having trouble, there we go. Step 4 is basically just to say how we're going to make it. Okay, so in this case, you take 1,590 grams of K3PO4 and enough water to make 2.50 liters. And that's how we would make this solution, using the idea of molarity. Okay. All right, now let's look again at our K3PO4. And we're going to use that to examine the concept of ion concentration. Now, sometimes we don't care so much about what we're actually looking for, and we'll do a conductivity lab at some point in time. I think it's this week. I have to look at my list. Sorry. We will do a conductivity lab where we're looking at how many ions are in solution and how that affects our conductivity, or our ability to conduct electricity. Many things depend on the number of particles in solution, not on the number of actual molarity. And ion concentration is one of those things. The conductivity of electricity is based on how many ions you have, not how many formula units that you have. Okay, so for example, let's take a look at potassium phosphate again, K3PO4. And in that last slide, we were at 3 molar. And that means that we have 3 moles of potassium phosphate for every 1 liter of solution. Okay, so what I want to know is, actually, let me not say how. Let's say, what is the concentration of our ions? Okay, so first of all, let's go ahead and break this up. If we have K3PO4, we have 3 potassium ions, and we have 1 phosphate ion in every unit, or every formula unit of potassium phosphate. Okay, so what we'll do then is we'll take this 3 times potassium and we will multiply that by our molarity. And what that means is that we have 9 molar potassium ions. Okay, and we could do the same thing here. 1 phosphate times a 3 molar potassium phosphate solution means that we have 3 molar for our phosphate ions. And then if we wanted to, we could combine these, and we could say that our total ion concentration is 12 molar. Now, if I ask for your concentration of ions, I want all 3 of these values, okay? Unless I specify that I only want 1, you should assume that I'm asking for all 3 of these, that I am asking for the potassium content and the phosphate content and the total content. So no matter what I'm working with, if I say, what's the concentration of your ions, I am looking for you to tell me the concentration of the ions individually and the total ion concentration. All right. So now, one of the things that we often do is that things are usually shipped to us in concentrated form, because why ship large quantities of water across the country, right? Okay, so a chemical manufacturer might make 3 molar or 6 molar or 12 molar, and that's what they send to the lab, except that you usually don't use 3 molar or 6 molar or 12 molar when you're working with something. Well, that's not true. There's times we use 3 molar, but a lot of times, like, let's say that you're working with acids and your stock solution is a 6 molar hydrochloric acid, but you're not usually going to use 6 molar hydrochloric acid. That's like super, super concentrated. So what we need to do is we need to take that stock solution and we need to make it more dilute. And so there's specific, there's a specific equation for what we call dilution chemistry. And that is our dilution equation. okay? And the dilution equation is M1 V1 equal to M2 V2, okay? And this is the initial molarity times the initial volume equal to the final molarity times the final volume. Now this can be really tricky. So remember that we had that solution before. I'm going to continue to use that. So let's say that our stock solution is that 2.5 mole, the 2.5 liters of a 3 molar potassium phosphate solution. Okay. We want to use this to make, let's say 125 milliliters of a 0.35 molar solution. And we want to know how to do that. Okay. Well, so what we're going to do is we're going to set up our dilution equation. So our M1 is our initial molarity. Our M2 is our final molarity. Our V2 is our final volume. And in this case, what we're actually solving for here is V1. And so it's easy to look at this and say, well, wait a minute, don't you have V1 right there, that 2.5 liters? And no, you don't. That's your large, gigantic, 2.5 liters is a lot. Okay, and that's your stock solution. That's the stuff that's sitting on the sideboard waiting to be used. And you're going to take a little bit out of that stock solution, and then you're going to add a whole bunch of water to it to make what you need. Okay. All right, so let's solve for our V1. And so then we would say that V1 is equal to 0.35 times 125. Notice that this is in milliliters. Okay, divided by 3 molar. Okay, so I have 125 times, and you can leave this in milliliters here as long as they agree. So 125 times 0.35 divided by 3. And you can see up here, oh, actually, the way I have this written right here shows only 2 significant figures. Okay. So if I have 2 significant figures here, then I can only have 2 significant figures in my answer. And so when I get 14.5833, this gets rounded to 15 milliliters. Okay. And that is my V1. So now here's how I write my final answer. My final answer will be written like this. Now this might be your SOP, and in the industry that stands for Standard Operating Procedure. And that's just a list of steps that you would do to make this. So the dilution steps for this might read, step 1, measure out 15 milliliters of our 3 molar potassium phosphate solution. And step 2, add. Okay, so notice here that we want to make 125 milliliters. So we say 125 minus 15 is 110. Okay, so add 110 milliliters of water. And you'll notice I put in my little decimal point here to indicate that that 0 is significant. And this is how I would work this kind of a dilution problem. All right. So now what we're doing is we're going to take a look at 3 different reactions that are going to be very important here for the rest of the chapter. The first one that we're going to be dealing with are precipitation reactions, and then acid-base reactions and redox reactions. But today we're just going to start with precipitation reactions. Okay, so precipitation reactions occur when we have 2 soluble aqueous, we have 2 soluble ionic solutions that form to make an ionic precipitate. Okay, I want to be really clear about that. Some people think, well, I made a precipitate, so it's a precipitation reaction. And no, that's not true. Sometimes you will get a precipitate out of redox reactions based on what you're working with. Okay, so in a precipitation reaction, what we do is we take 2 soluble ionic solutions and mix them to form an ionic solid, or an ionic compound that is a solid. Okay, and this solid is called a precipitate. There's a horrible joke that says if you're not part of the precipitate, you're part of the solution. Or if you're not part of the solution, you're part of the precipitate. So, you know, there's a lot of chemistry humor out there. Okay, so the precipitate is that solid that comes out of solution. So in order to be able to predict that, one of the things that we need is we need to be able to identify what is soluble and what is not soluble. And there's a whole bunch of those in the slides, in the annotations, extra links and documents to help you with this. Before we start talking about that though, let's list a few things. If we say that something is soluble, that means that all of it will dissociate in water. Okay, so what that might mean is something like, let's say, sodium nitrate, NaNO3. So you will find out going forward that sodium and nitrate are those always compounds that are always soluble. Okay, so that means that in the presence of water, 100% of this will become sodium ions and nitrate ions. Okay, all of it, all gone. All right, so now let's take a look at some other things. Insoluble, whoops, insoluble has an N in it. Insoluble, okay, means none will dissociate in water. Okay, so an example of that might be, let's see, here, where's a good one? All right, a good example of that is lead 2 chloride. Lead 2 chloride is PbCl2. Notice it's lead 2 and not lead 4. Lead 4 is not insoluble, quite like lead 2 is, but lead 2 insoluble in water. All right, so PbCl2, solid. If we drop that into water, we will still have PbCl2, solid. nothing interesting happens. You take your solid, you plop it in the water, and there you still have a solid in water. And that's an example of something that's insoluble. Okay, now let's look at a weird middle ground, and that is what we call marginally or slightly soluble. An example of something that's marginally or slightly soluble might be calcium hydroxide. And you'll be able to predict all these in a minute. Calcium hydroxide, CaOH2, solid. So what does it mean to be slightly soluble or marginally soluble? It means that when we add calcium hydroxide to water, we will get some calcium ions, Ca2+, and we will get some hydroxide ions. And this is really important, we will get still some solid calcium hydroxide. Okay, so usually what happens is that this is just a small amount is soluble, but most of it will stay solid. And what that means is that in a reaction, this will precipitate out. So sometimes you'll see calcium hydroxide listed as a tiny bit aqueous, but most of the time it will precipitate out. Because of that, if I ask you for something that's insoluble, or I ask you for what will precipitate out, you need to include marginally soluble and slightly soluble in your insolubles. Because even though some of them will dissociate in water or come apart, most of them will not. And so it's very important that marginally and slightly solubles be linked with those insolubles. Okay, so let's take a look at some of our rules. Actually, I'm not going to take, there's actually a lot of stuff in the slides and annotations for the rules. So what I want you to do is, if you haven't read the slides or annotations yet, I want you to pause the video. I want you to pull those up, take a look at them real quick, and then come back to this so that we can just practice this. Okay, so based on that, let's take a look at a variety of things that work with that and how that might work. Okay, let's say that we have PbNO3 2. Let's say that we have PbSO4. Let's say that we have AgNO3. Let's say that we have AgCl and our ever-present sodium nitrate. Let's look at cobalt 2 chloride, CoCl2. Let's look at a few other ones, and let's look at COOH2. And last but not least, Pb3PO4 2. Okay, so again, I want you to have all of your information from the slides about solubility now, and let's take a look at what that means. Okay, so first of all, what we need to do is we need to go through and we need to separate things. So Pb, this 2 here, means that we have lead 2 and nitrate. Okay. Now we have a rule, if you're looking in those, rule number 1 says that all nitrates are soluble. And that's our rule number 1. Therefore, this first one, lead 2 nitrate, will be soluble. Okay, now let's look at our next one here. We have Pb 2 plus, and SO4, 2 minus, lead 2 sulfate. And I'm just looking to make sure that I can remember which ones. Now, rule number 4 says that most sulfates are soluble, except barium, lead 2, mercury 1, and calcium. That means that this is insoluble because it's an exception to that rule. So PbSO4 is going to be insoluble. And I'll go ahead and insoluble. And this one is soluble. Now let's look at AgNO3. Okay, so now we have silver and nitrate. Now you'll notice I said, oh, we've got that nitrate in there. Nitrates are often used because they make everything soluble. So they're really useful. So again, this is our rule number 1. And that says then that this one has to be soluble. Okay, but now let's take a look. Here we have silver chloride. Okay, Ag plus and Cl minus. Now, if you look at rule number 3, rule number 3 says most chlorides, bromides, and iodide salts are soluble, except with silver, lead 2, and mercury 1. So hopefully you're seeing a trend here. Mercury 1, lead 2, silver, these are things that are going to make our anions insoluble unless we're putting them with nitrate. Okay, so that means that this one, because of the silver with the chloride, is going to be insoluble. Now we look at our NaNO3. Okay, so sodium plus and NO3 minus. Sodium nitrate is used often because sodium nitrate is always soluble. And it's always soluble for 2 rules. Rule number 1 and rule number 2. So both the sodium and the nitrate make this completely soluble. So yay, we know that this one will dissolve in water. Okay, well now let's take a look at the next one. And for the next one, see we have that 2, so we know that this is CO2 plus, which is cobalt 2, and chloride. So for that, let's go ahead and take a look at our rules. We have a rule for chloride, and the rule for chloride says that most chlorides, bromides, and iodide salts are soluble. Okay, and it's not one of the exceptions. So even though we see that cobalt and we think, ooh, that looks weird, it's totally fine. Okay, and so that means that by rule 3 about our chlorides, that cobalt 2 chloride is soluble. But now let's take a look at what happens when we put it with hydroxide. We have CO2 plus and OH minus. Now, according to rule number 5, most hydroxides are only slightly soluble. Sodium hydroxide and potassium hydroxide are always soluble, and so is ammonium hydroxide. But ammonium hydroxide is really just like ammonia in water. Okay, ammonium hydroxide, sodium hydroxide, and potassium hydroxide. And then we get barium hydroxide and calcium hydroxide are marginally soluble. But hydroxides really aren't very soluble, okay, especially when we get away from the alkali metals and some of the alkaline earths. So what this means is that while a tiny bit of it might go into solution, most of it is not. Most of it's going to precipitate out, which makes this insoluble, even though it's listed as slightly. All right, now our last but not least, we take a look here and we see Pb3PO42, and this 2 down here means we are dealing with lead 2. This should be kind of an automatic red flag. Lead 2 is often insoluble. And here we have it with phosphate. And if we look in this case at rule number 6, we will see that most sulfides, carbonates, chromates, and phosphate salts are only slightly soluble, except for those containing the cations in rule 2. Okay, well, that means that not only are phosphates slightly soluble, but it's paired with lead. And lead does not like being soluble, which means that this one definitely, Pb3PO42, will be insoluble and will precipitate out. Okay. I think I have one more topic in this section. I apologize. I hope it's not in this next section. I don't have that in front of me, but let's go ahead and do it. And if it's for next week, then you'll already have seen it. And that is the idea that whenever we're doing precipitation reactions, we have 3 different ways of describing them. Now, I actually made 2 videos last semester and posted those, and those are in the correct week, which might be this week or it might be next week. And basically the reason I did that is because even after my lecture video, students had a lot of trouble with this. And so I made a couple of additional videos looking at just those 2 things and some special cases involving them. And students said that they were really helpful. So if you're stuck on this next section that I'm going to show quickly, watch those 2 videos and I think you'll probably be unstuck. Okay, so first of all, we have what's called a molecular or a formula equation. Sometimes this book refers to them as formula equations, though I've usually seen them referred to as molecular equations. And formula, because ionic compounds are always formula units, not molecules, but they're called molecular equations because we're going to write everything as though it were a molecule, even though it's not, and that'll make sense in a minute. The next step that we have is a complete ionic equation. And in the complete ionic equation, what we have is we have everything that's in an aqueous form is separated into 2 different ions. And the last thing that we will have is our net ionic equation. And in the net ionic equation, what we're doing is we're looking only at the pieces that react. Okay, so let's take a look at what that might be. Let's write down kind of an official piece as though you might see it in what you're working with. Okay, so I'm looking for one. There we go. Okay, so here's a problem, and it says we want to write the molecular formula equation, the complete ionic equation, and the net ionic equation for the reaction between cobalt to chloride and sodium hydroxide. Okay, so let's take a look at this. First, we have cobalt to chloride, which is going to be CoCl2. Okay. And sodium hydroxide, NaOH. Now I go right to my my rules, and I see that based on chlorides, this is going to be soluble, and based on the sodium, this is going to be soluble. So I can write a little AQ after each one. Now, I often find that it's easier to do the end of this if you start with the complete ionic first. Okay, so we'll say, okay, well, let's say that I have my cobalt ions and my chloride ions. Notice I'm not doing any balancing until I'm done. Okay, I have cobalt ions and chloride ions. Okay, and all I've done is break this one apart. Now I take a look at the sodium hydroxide, and that means that I have sodium ions and hydroxide ions. Okay, now let's take a look at this. Now what you do is you say, okay, well, I know that my cobalt and chloride together are soluble, and I know that my sodium and my hydroxide together are soluble. So what happens if I switch them and put the chloride with the sodium? Well, I know that chlorides are soluble and sodiums are always soluble, so that's not going to be it. So those are going to stay as ions on this side of the equation also. Okay, so I know that those aren't going to come apart. Okay, so now I take a look at my cobalt and my hydroxide. And I do see that hydroxides tend to be insoluble or slightly soluble, which means they're going to precipitate out. And that means that my cobalt and my hydroxide together, COOH2, is going to be a solid. And I'm just going to kind of underline it here so that I can see that. And now what I do is I come up here and I'm going to put them together. Now the sodium chloride is going to stay aqueous. Okay, but my cobalt hydroxide is a solid. And so that gets reported like this. And again, I'm going to underline it just so that you can keep watching it. So here you'll see that the solid stays together all the time. Okay, now at this point, what I'm going to do is I'm going to go through and I'm going to balance it. And I look at the top here and I see that I have 2 chlorides in my cobalt chloride. So I'll go ahead and put a 2 right here on my sodium chloride. And then I see that I have 2 hydroxides here, which means that I know I'm going to need 2 in front of my sodium hydroxide here. Usually these are that simple. You just balance it out and it comes right out. So I have 1 cobalt, 2 chlorines, 2 chlorines, 2 sodiums, 2 sodiums, and 2 hydroxides and 2 hydroxides, and I'm done. But that means that I need to come down here and I need to make sure that my complete ionic equation matches. So I have 1 cobalt, but here I have 2 chlorides, so I need to put a 2 here. 2 sodium hydroxides means I need 2's in front of those. And then I'll need a 2 in front of this sodium and a 2 in front of this chloride and nothing in front of my cobalt hydroxide. Great, now I'm balanced. And what I can do is I can move on to my net ionic equation. Now for my net ionic equation, I am only looking at the ions that are making the solid. And that's the cobalt and the hydroxide. And what I can do then is I can leave everything else out. And so I'll say CO2 plus aqueous plus 2 OH minus aqueous yields COOH2 solid. Okay? I look forward to seeing you in recitation.